Everyone, welcome back. Let's continue with the second part of the video. Those who haven't watched the first part, I would highly recommend doing so in order to fully understand the topic. The link of the first part you can find in the description below. Sometime you need to update individual uh, tab. It has been updated. Now move to setup, double click here, double precision. It is already 2D as we had selected in geometry 2D and have 4 cores and start. Now Fluent has been opened, so let's do our simulation setup and run one simulation and see how we can go further. So first of all, in general, it is steady state simulation and we are not using any gravity. In model, viscous model with K omega SST, I'm leaving it as default. We don't need any other equation. For material, fluid is air, and let's select water as our fluid. Using Fluent database, water liquid. Okay, copy and close. Close solid, we don't need any solid. Cell zone, the fluid should be water. Let's see if it is water. So by default it is here. Let's make it water. Apply and close. And another thing, I want to change units. For fluid inlet, I want to have in mass flow rate. So for that mass flow, convert it into gram per second. The other thing, I need length, convert into millimeter and close. Okay, now boundary condition. Inlet is the velocity inlet. Let's convert into the mass flow inlet. Let's provide a mass flow rate as 20 gram per second. You can also define as a parameter. You already know that if you have seen my previous video. Otherwise, you can look into my previous video. Anyway, 20 gram per second normal to the boundary and turbulence as it is. Apply and close. At outlet, we don't need to define anything or any other boundary we don't need to define. Now, we want to see the mass flow rate in individual parallel channel. So how we can do that? For that, we need to define a surface on each channel and need to define report definition mass flow rate on these surfaces. So for that, go over here on create and it's a 2D, so surface would be a line. So therefore, we will create a line. You should know the coordinates for the line. For example, from here to here. So for line, you need 2 points. One is x1, y1, x2, y2. I have already noted down those coordinates and you need to know for your geometry. Anyway, our center was over here. It means the y will always be 0. So leave y always 0 and we just need to define x and x1. So for first one, it will be minus 34 and minus 27. These are in millimeter. That's why I had converted into millimeter. Otherwise, I had to write in meter. That would be with decimal. So I wanted to avoid. Let's call it line 1. Create. Line 1 has been created. So you can see later. So give it a name line 2. And second will be minus 19 to minus 12. Create. We have defined line from here to here, here to here, here to here. So for every parallel channel, we have defined line. Now we will go to the report definition and surface report and mass flow rate. I have detailed video about report definition. You can look that video. So anyway, mass flow rate 1. So here you can see line 1, 2, 3, 4, 5. So line 1, just select these two and create output parameter. So okay, now we can copy this one, deselect these two, create output parameter, mass flow rate 2 and line 2. Okay, now we have defined all these reports. So or our output parameter. If you go to the workbench, you can see all these will be here. Mass flow rate 1, 2, 3, 4, 5. So here we can see the flow rate for different inlet and outlet diameter. Anyway, one more thing I want to do, that I want to create one plot where I want to have all these so that I can see how all these are changing. I'm not giving it any name, and I will say okay, that's it. So we have defined everything, and one last thing, define number of iteration. Let's call it 500. So here you can just initialize and go out and run different simulation, or just let's run one simulation over here. Initialize and create. Initialize and calculate. It is initializing and calculating. So let's see how our results will look like. It is initializing. So I just use hybrid initialization. So you can do whatever initialization you like, or whatever suits your simulation. Here you can see flow rate in different parallel channels. So mass flow 1, 2, 3, 4, 5. So you can see they are not same. Just as a background, so you get equal distribution when you have main inlet much bigger than these branched channels. So that we will see in a minute. I have already run all those simulation and we can see. Okay. Meanwhile, this simulation is running, so let's check out results. I have already run this simulation, so let's check out the results. So if I go to the parameter set, and here you can see these are the results. I have run for 10, 20 and 25 inlet and outlet diameters. And here you can see these see, results are complete. Okay, anyway, here you can see for 10 millimeter the flow rate 37 gram, 35 gram, 40 gram, 48 gram and 36 gram. So here is minimum is 37 and maximum is 48 gram. So there is a difference of 9 grams, approximately 25%. But for 25 millimeter, you see 38, 39, 40, 41 and 39. So a difference of 2 grams. So these are quite close to each other. So you can see as the diameter of the main inlet and main outlet are increasing, you are getting a better flow distribution. And that's what we can see over here. In here we had here 5 millimeter and 5 millimeter, and you can see where here you can see there is a lot of difference in the flow distribution. So anyway, now how you can run rest of the simulation for that, that was 10 millimeter. Anyway, you can, for example, here define 15, 15 and 15, then for example 25 and 25. Whatever parameter you want to run, you can define over here. So it means now it is changing the inlet and outlet diameter in your geometry. So it will change these diameter in space plane in geometry. Then it means it need to update meshing, so it will go to the meshing, it will update meshing accordingly, then it will come to the setup and will run all these simulation. So you don't need to go all these steps one by one. So you have defined all these parameters, you will go over here and you will say update all design points, and it will run all these simulation one by one, and it will go in individual tab and run all these simulation, and you will get end results like that. So in the end, let's just open the last one to show you how these results looks like. For that, let me set it as a current, because if I will open this one, so it will open current, so it will open this design point 0. Now I made it current to design point 2. Now it will open this one. So go to the project and let's go to the results. Okay, here is I had defined one line, so let's deactivate this one and plot a velocity contour. Velocity, yes, all domain. Okay, let's select all, and we want to plot velocity, and let's plot it with 100, and okay. So here you can see the velocity profile looks similar in all these branch channel. So yes, so and you can see here it looks much bigger, so it is 25 millimeter. So either you can make this one bigger or this one smaller to get the equal distribution. There are a few other ways, but anyway, you can look into theory. So that's how our results look like, and I think that's it for this simulation. I hope you like the video. If you have any questions or any query, leave them below. Thank you for watching, and see you in the next video.